Uh, Hello students. So today we'll see actually the TM modes for parallel plate waveguide. In the last class we saw uh, for the TEM mode and the TE mode. Okay, so in a similar way actually we'll be defining same parameters when we are analyzing the parallel plate waveguide for the TM mode. Fine. So let us start with the differential equation what we studied actually in the last classes. So I believe you remember this equation. This is dou square easy over dou x square. Definitely this is a function of space xy plus dou square easy xy dou y square plus kc square easy xy is equal 0. Okay, so we have here these equations, okay, in terms of the longitudinal electric field component for the TM mode. Okay, now we know certain things, so let us recall. So here we are kc square is actually k square minus beta square, and if you remember we took assumption this, okay, the width is very greater than 2, the separation between the two plates. Okay, so with this assumption actually if you go, so you will find that the field variation with respect to x is negligible. Fine, means what I'm saying that the field variation with respect to x, okay, fine, is negligible. Fine, so if we have this assumption, then yes. Now the thing is it directly affect the this differential equation. Fine, so now with this assumption one can easily write, okay, rewrite this equation as dou square easy xy dou y square, okay, plus kc square easy xy is equal 0. Fine. So right now we have this equation, okay, where we are recording the variation, okay, or the change in variation actually in a y direction. Fine, so yes, for this equation one can definitely write a solution, okay, a general solution we may write here, and in a similar sense what we did for the TE mode. So if you're writing this thing, this is easy is a function of xy is equal a sine kcy plus b cos kcy. Fine, so this solution we may use here. Fine, now let me take a new page here. Okay, so let us write down the complete field equation ez component here. Okay, so considering all this xyz variation, these things, so ez is a function of xyz is equal to, we may write the solution what we are going to use here. Okay, it is a sine kcy plus b cos kcy. Fine, and the wave is traveling in z direction because we took here the z also, so this is e to the power j beta z. Okay, now the thing is like if you see here, this constant a and b actually may be found, okay, by applying the proper boundary condition. Okay, so if you know the boundary condition, yes, you can obtain this a and b. Fine, like we did similarly for the TE mode. Fine, now so as we aware, this parallel plate waveguide, okay, is made of with this PEC, perfect electric conductor, and so particularly we can see at on the plate actually, bottom plate and the top plate. Fine. So how we can write these things? Okay, so yes, we can write here this components like this: x component, x 0 and z is equal to, okay, means I'm writing for y is equal 0 and y is equal d. Fine. So the field component will be 0, the x component of the electric field will be 0, and also the x component at x, d and z will also be 0. Along with that, actually there is a one longitudinal component will be 0 here, like this: ez, okay, x 0, z is equal 0, and ez x 0, z is equal 0. Fine. Okay, hopefully this is clear to all. Fine. Now we aware here that this x component, okay, of the TM mode actually is related with the easy component. Okay, so yes, we may recall this thing. This is Ex as minus j beta over kc square dou Ez over dou y. Fine, and this will be 0. Fine. So you need to recall actually from the previous classes this all the components here. Now what we can do actually, we can recall these boundary conditions actually over here. Fine. And then yes, we can obtain this constant a and b, as well as some relation for the kc also. Fine. So now let us apply this things boundary condition here, and let us see what will happen. Okay, so let me take a new page here once again. So yes, so this is easy, okay, x comma 0 comma z, okay, is equal to, like if you are making y is 0 here, okay, so you see here these things, this particular part, okay, so the moment you are putting y is equal to 0, okay, so this term will be 0, whereas you left with only this term. Okay, I'm talking about this term. Fine. So you left with this term. So let us write down this thing. So this will be what? B e to the power minus j beta z, and this is supposed to be 0 as per the boundary condition, like this thing. Now from here we can make a conclusion here, like this b is equal 0. Okay, now let us recall another boundary condition, which is x dz. Okay, and in this case b is already 0. Fine, so b is already 0, so you can remove this one, and you left with a sine kc y. Fine. So how we can write these things? A sine kc d, okay, and of course e to the power minus j beta z, and this is supposed to be 0. Fine. So from here actually we may get a conditions actually, and what is the condition? The condition is that this is kcd, okay, is equal to n pi. Fine. Yes, in a similar sense we got last time also, and here n is 1, 2 and 3. Fine. So right now, like we have the sufficient things here to reconstruct once again the easy component. Okay, and if you are writing this, so this will be easy, okay, is a function of x, y, z is equal to b is 0, okay, because we are finding the things for integer n here. So what we can write? A n, okay, sine n pi y d e to the power minus j beta z. okay, where this an is actually the amplitude constant, and this is associated with the discrete Tm and mode. Fine. Now once you have this easy, actually now you can use actually those relation we obtained in the last classes actually. Okay, we can obtain other field component like hx, okay, hy and ey. Okay, if you see these things, so we derive this component in terms of easy component. So right now we have this easy actually, correct? Okay, so with this one can easily find it out the rest of the component. Okay, okay, so let us write down these component. Okay, so I think, so let me take a new page here. Okay, so this was the equation. Fine. Now writing the other components. Okay, so let me first write hx, and this was j omega epsilon by kc square, okay, dou easy over dou y. Fine. So yes, you can recall this here. Okay, and if you are differentiating with respect to y, so this will be j omega epsilon over kc an cos n pi y by d e to the power j beta z. Fine. Another is that hy, so this is minus j omega epsilon over kc square, and this is you are differentiating with respect to x, so yes, this is 0. Fine. And the last one is ey is equal minus j beta kc square d dou ez over dou y. Okay, so if you are differentiating once again, so this is j beta kc an cos n pi y by d e to the power j beta z. Okay, so right now we have all the component here. Okay, so now let us define here some other parameters. Okay, so as we got the conditions, okay, this kc is equal n pi by d. Fine. Okay, so this was the same actually earlier for the t mode also, so this is actually the same cutoff wave number, okay, for TEN modes. Okay, fine, and also the TM modes. Fine. So yes, you can write the cutoff frequency as, okay, in the same sense actually. So I'm directly recalling the expression actually. This was n by 2d under root mu epsilon. Okay, and beta is under root k square minus kc square. Fine. So you can write these things k under root in terms of the cutoff frequency, which is fc by f to the whole square. Fine. So it's very important role here, this cutoff frequency. We are defining all the things. Okay, so now the thing is, here you can see for the TEN and TMN mode, okay, both the modes having the same cutoff frequency. Okay, but there is another thing, like you should note it, that we cannot propagate, okay, one mode without other, okay, because they have the same cutoff frequency. Fine. So now let us define here once again the wave impedance for the TM mode. Uh, so recalling those relations, remember this was TZ TM is minus EY over HX. Okay, so we already have this EY and HX. Fine, and these are the non-zero quantities here, and it would give you some expressions. Okay, like this. This is beta eta over k, and the k you already have in terms of the cutoff frequency. So yes, you can write these things like this. The final will be eta under root 1 minus fc over f to the whole square. Okay, so this is the wave impedance for the TM mode. Fine. So okay, so now right now we have all the field components, okay, and the cutoff wave number, cutoff frequency, beta, and all for both TE and TM mode. Now let us somewhat focus on the phase velocity and group velocities, and the wavelength. Okay, when the propagation happening inside the waveguide. Fine. So let us write down here the phase velocity. So yes, just a minute. So let us waveguide phase velocity. Right. So we can define these things as omega by beta. Right. We all aware about these things, and yes, you may write these things omega by k under root 1 minus fc over f to the whole square, or you are also free to write like this 1 upon under root mu epsilon divided by under root 1 minus fc over f to the whole square. Fine. So we can make a certain conclusion here, and it is really very important actually. Why? If you see the phase velocity for propagating mode, okay, whatever the mode is actually, basically I'm talking f is greater than fc, okay, this propagation, these things, okay, you will find that the phase velocity, okay, is larger than the phase velocity of the plane wave propagating in a media defined by like this mu and epsilon. Fine. Now if you see in case of the plane wave, okay, like if you're considering only the plane wave, fine, so the phase velocity and it is important to know here this phase velocity. What is the phase velocity? The speed at which the points of the constant phase on the wave moves. Okay, so basically for the plane wave, the phase velocity is equal to the velocity of wave. Okay, we aware about this thing, but for the waveguide actually, for waveguide, when all these propagations are happening in this waveguide, so there actually the phase velocity is not equal to the speed at which the overall wave propagates along the guide. Basically this overall wave propagates means like you can assume these things as the group velocity. Okay, so this will be talking about later actually. Okay, so definitely, so this phase velocity is not equal to the speed at which the overall wave propagate along the this waveguide or parallel plate system actually. Okay, so like if you see actually the more details of these things, so we may once again recall, okay, those equations, and from there actually we can conclude some facts. Okay, So if you remember this equation where when we started the making the solution of the differential equation, so you got actually the two terms, okay, which is a sine and another is sine kcy and cos kcy. Fine. And kc we just got actually after applying the appropriate boundary condition. So now separately we can see actually how mathematically they linked actually. Fine. So let me recall this sine. Okay, in place of kc I am writing these things. Fine. And e to the power j beta v. So this was one term. Another term was cos n pi by d e to the power j beta. These were the two terms, remember, when we started our discussion of uh, making the solutions actually for that differential equation. Fine. So if you a little bit open up these things, so you can write these things as e to the power j n pi y over d minus e to the power minus j n pi y by d, fine, divided by 2j, and of course e to the power minus j beta z. So finally you can write like this is 1 by 2j, okay, and e to the power j n pi y by d minus beta z minus e to the power minus j n pi y by d plus beta z. Fine. Yes, we can write. And similarly, this equation can be also written, okay, half of e to the power j n pi y by d minus beta z plus e to the power minus j n pi y by d plus beta z. Okay, so you can see there is a two mathematical functions. Okay, these are mathematically equivalent if you see carefully these things. Okay, and how you can see these things. Okay, first of all, for this first is mathematically equivalent. Okay, and these two planes actually, okay, two plane waves particularly propagating along the guide, okay, at angle defined by the component y and z. Fine. If you see here, okay, so these two actually define this angle actually, and the wave is happening inside the parallel plate system. Fine. So what we can conclude here, like the wave on the this parallel plate system, okay, or parallel plate waveguide, actually, like, it looked like the superposition of two plane waves, okay, and it is being reflected between the two plates as the propagation happens. Fine. So one is this, another is this. Fine. So you can see like this, okay, because our solution we assume, okay, in this manner. Fine. Now let us define some other components too, correct? So for propagating mode within the waveguide, fine, the phase constant is related to the wavelength within the guide. How we can relate these things? It is beta is equal to 2 pi by lambda g. Fine. So in this way we are relating these things, and yes, you are always free to write in terms of the cutoff frequency, and if you can little bit do some exercise here, so you can write lambda by under root 1 minus fc over f to the whole square. Fine. Okay, so this is what So this is the wavelength within the waveguide in terms of the cutoff frequency. Okay, and here the lambda is the wavelength of the plane wave propagating in a media defined by this materials what you have selected, maybe in journal mu and epsilon. Okay, and for propagating mode, okay, when we have the propagating mode, when f is greater than fc, the guide wavelength is longer than the corresponding plane wavelength. Fine, I'm saying that the guide wavelength lambda g, okay, is the longer than the corresponding plane wave wavelength. Fine, so this is one conclusion here. Another is that you can define the lambda c also, okay, which is so called as a cutoff wavelength. Okay, cutoff wavelength. Okay, lambda c. How you can define? So we already aware these things. Lambda we can write down like this, 2 pi by k, right? So why not lambda c is equal to 2 pi by kc. Fine. So if you little bit solve this, okay, this will be 1 over fc under root mu epsilon. Okay, so the lowest frequency for T and T or TM mode, and we aware this thing that for both the modes this frequency is same, means cutoff frequencies for both T and TM are same. Fine. So now if you see fc for n is equal to 1. Fine. So how we can write these things? 1 upon 2d under root mu epsilon. Okay, so which gives actually the cutoff wavelength as lambda c is equal 2d. Okay, and what is the d actually? This is a separation between the two parallel plates. So it means what? That for TE1 and TM1 modes, okay, for the parallel plate waveguide, the lambda c is 2d. Fine. So these are the some of the general information about these things, and the same will be actually when we deriving for the waveguide system. Fine. So the idea of this analysis that we can use the facts, okay, when we are deriving the practical waveguide system, now. So right now if you see, actually we defined a number of things, and especially we try to derive the field components, impedances, beta, okay, and the cutoff frequencies. We written all the things in the cutoff frequencies for all three modes, TEM mode, TM mode, and TE mode. Fine. But all the analysis whatever we did, actually it was like that we started our discussion as a lossless system. Fine. But in practical scenario, actually it would be like you supposed to accommodate the losses. Fine. So what we'll see, actually we'll see some of the things when we have the losses in a waveguide. Fine. And these losses, actually, like there are two kind of losses. Okay, one is this conductor, and another is dielectric loss. Okay, so let us focus on the conductor and dielectric losses in waveguide system. Correct. So we have enough number of data, okay, or enough number of things, actually what we derived in the previous classes. So basis on that, one can easily calculate these losses. Fine. So now we started these things e to the power minus j beta z. Okay, the propagation means like the gamma is alpha plus j beta, where we completely ignored the alpha and we started all the things e to the power j beta z, the lossless system. Fine. So it means that when the losses are incorporated, fine, or when we have the lossy system, the form of the jet dependent wave propagation terms must be modified. Okay, how it is modified? In place of beta, actually you have to recall the gamma once again, means e to the power minus gamma z. Okay, and we aware about the fact this gamma is alpha plus j beta, or this could be again expanded like this, alpha plus alpha d plus j beta. Okay, so what is that? This alpha c is actually the conductor losses, this is actually the dielectric losses. So this is conductor losses and this is dielectric losses. Fine. Now here we supposed to estimate this alpha c and alpha d. Fine. So these are the new things here for us. Fine. So basically, like to determine the conductor losses, okay, we are employing the perturbation method. Okay, so we'll be talking about this perturbation method in detail, okay, when we start the cavities, waveguide, this cavities, circular or rectangular cavities. Okay, so perturbation method actually it requires particularly field distribution within the waveguide. Okay, okay, as the name suggests, the perturb, okay, you need to if you are making some changes in the fields for a particular mode, okay, that's supposed to be recorded. So since we know the different mode have the different field distribution, okay, for the TE mode and TM mode, and in this also there are the other variations too. Okay, so we have the different field variations, the distribution, sorry, and definitely if this is so, we can say that each mode will have the different attenuation constant due to the conductor losses. Okay, again I am repeating that each mode will have different attenuation constant due to conductor losses. Fine. So with this background, okay, let us start the analysis and finding the dielectric losses separately and the conductor losses separately. Fine. Okay, so let us start with the dielectric losses. Fine. Now the thing is, if we are only incorporating the dielectric losses, okay, within the waveguide, then we may write the propagation constant like this, means gamma is equal alpha d plus j beta. Fine. If you are only actually incorporating this time the dielectric losses, and this could be further written as kc square from the previous equations like this. You can also free to write like kc square minus omega square mu epsilon. Okay, another assumption is that the magnetic loss in the dielectric is assumed to be very small, okay, or negligible. So in that case you can write mu is equal mu naught. Fine. And epsilon, okay, the permittivity could be written as relative permittivity epsilon naught 1 minus 10 delta. Fine. So this is a very obvious relation. Okay, we are recalling for the permittivity. Now in total actually the propagation constant could be rewritten like this: kc square minus k square 1 minus j 10 delta. Fine. Or you can also write these things as kc square minus k square plus j k 10 delta. Fine. Okay, so where this k square actually, if you see this k square, particularly omega square mu naught epsilon r and epsilon naught. Okay, this is a square of the real wave number, for the dielectric without these things. Now once again we can rearrange these equations, okay, this equation, and we can conclude some of the things here. Okay, so let me take a new page here. Okay, so if you can common it out, this kc square minus k square, I hope you are writing along with me also. kc square minus k square under root 1 plus j k square 10 delta divided by kc square k square. Fine. Yes, we may write these things. Okay, there is no harm of writing these things. Fine. Okay, now so if we can do kc square minus k square is equal to like this, minus k square kc square, we may write as minus j beta square, or you can write j beta only. Okay, this is for both. Okay, both means for TE mode and TM mode, both mode. Fine. So finally gamma could be expressed like this: j beta under root 1 minus j k square 10 delta over beta square. Now why we are writing like this actually, if you see we have the beta here in this equation, and we have a 10 delta losses representing the losses actually, and the k square. Fine. So it easy our life. Okay, now the thing is because after that actually, if you see, we cannot solve this equation mathematically. So definitely we supposed to put some assumptions here once again. So if let's say the dielectric losses are small, and usually in practical system actually you will see these dielectric losses are small. Okay, so what we can say that if dielectric losses is small actually, so this 10 delta, okay, loss tangent is small. Fine. If it is so, correct, so what we can say, we can use a series or approximation of 1 minus x as 1 minus x by 2, where x is very less than to 1. Fine. So this applies here actually. Okay, and finally it will be like this: gamma is close to, okay, this will be j beta 1 minus j k square. Okay, the same equation I'm writing, 10 delta over beta square. Fine. This under root these things, okay, is here, this 2 beta square will be there. Fine. So finally, like, you can also write these things as k square 10 delta over 2 beta. Fine. plus j beta. Fine. And finally you can equate with alpha d plus j beta. Fine. Now if this is fine, okay, so the attenuation due to the dielectric losses for both TE and TM mode in any waveguide, this parallel plate system actually we are talking about right now, this will be alpha d is equal k square 10 delta over 2 beta. This is Napier per meter, and this equation is true for TE and TM mode. Fine. Now, like if I ask you to write this alpha d for the TEM mode, so what changes will be there? Okay, the changes only will be beta is equal k, because for TEM mode, okay, we have beta and k are equal. Fine. And in this scenario, okay, alpha d will be k times of 10 delta loss tangent divided by 2 Napier per meter. So this equation is for only TEM mode. Fine. So with certain approximations, actually right now we got actually this alpha d here finally. Now in a similar way, the conductor losses could be accommodated. Fine. So for the conductor losses, okay, we'll be talking about those things in a next class. Fine. So this is all about for this class, and you can see some of the critical dielectric, okay, and what is the loss tangent. It will be really helpful to check actually how, like, what level of losses actually there in the dielectrics. So basically when we are talking about the dielectrics in microwave engineering, so this is mainly the ceramics, and the ceramics actually having very low loss tangent, usually the order of 10 to the power 3 and 10 to the power minus 4. And along with that, nowadays in many system people are using the composites. Okay, these composites are made of this polymer and the ceramic also. It creates some these are the actually somewhat you can say porous actually with respect to the pure ceramic. So here due to this you will experience the losses are quite high as compared to the ceramic one. Okay, so this is in order of 10 to the power minus 2. Okay, so fine, so we'll be continue with the conductor losses in the next class. Thank you so much.